Okay, continuing on in Chapter 3, the next topic needs to go further in our learning objectives to talk about the Octet Rule. Some of you may have heard of this. And what does that entail? Okay, the Octet Rule is something we will use to discuss patterns for main group elements. The transition elements are always a little more confusing. The Octet Rule then tells us that main group elements tend to undergo reactions that leave them with 8 electrons in their outer shell. The valence shell is going to be 8 electrons. And how does that work out? So things like hydrogen will lose 1. Well, that's not going to leave them any electrons. But the hydrogen hydride ion, gains 1, and it ends up with an electron configuration like helium. The lithium and beryllium ions with +1 and +2 charges end up with exactly the same configuration as helium. Then if you take an electron away, 1 from sodium and 2 from magnesium, those both end up with the same electron configuration as neon. But if you add electrons to oxygen and fluorine, that is the same as neon. So they're going to gain and lose electrons to end up with 8 outer shell electrons. Finish the pattern here. Aluminum is going to lose 3 electrons and end up with only 10, just like neon. So the patterns here are they're going to explain how you get the particular ions that are common and stable. There's a few that are noted in here with asterisks, and that would be the group 3A elements that have D shell electrons in their outer shell, and they're not true noble gas electron configurations because they've got an additional D filled subshell, but at least the pattern of how many electrons are lost is very similar. This is a good way to remember which ions form for each element. It works quite nicely. The patterns are very helpful and consistent for main group elements. So the main group elements are going to undergo reactions, whether they're making ions and later for covalent compounds, that leave them with 8 outer shell electrons, and that gives them a noble gas electron configuration with filled S and P subshells. Filled in the S and P subshells for a valence shell. And so metals, what are they? They're on the left side of the periodic table. They have low ionization energies. They lose electrons easily, and they have low electron affinities. They don't gain electrons at all readily, and so they're going to tend to lose at least 1 electron. That's what they do, and they end up with that noble gas electron configuration because of their low ionization energies and poor electron affinities. What about the other side of the periodic table? Well, our friends, the nonmetals, are going to have the opposite then. They will have high ionization energies. In other words, they don't lose electrons very readily, but instead they have high electron affinities, high negative values. And so instead, what do? They're going to tend to gain at least 1 electron, depending upon what it is that it takes them to get to the position of, or this situation of having a noble gas electron configuration with filled S and P subshells. It becomes very stable. We can use this to predict the formation of ions, and it's very helpful. So whatever you do, don't go through life 1 electron short of an octet. You better study chemistry. Get it. Don't miss out. So according to the Octet Rule, what charge would an aluminum ion exhibit? Well, this is a multiple choice question. Think about it. So aluminum is in group 3A, and that means it is a metal. Aluminum is just like you think of it off the roll in the box from the grocery store. And group 3A elements are going to lose 3 electrons to get to a stable noble gas configuration. Which one is it for aluminum? Aluminum is element number 13. So it has 13 protons, right? And so if it's going to lose 3 electrons, the stable noble gas electron configuration is going to be the same as element number 10, which is neon. So losing 3 electrons gives you a +3 charge. That's what it takes. All right, what about the oxide ion? Oxygen, O2 minus. What electron configuration would be correct for the oxide ion? Oh, well, we've got to make sure we think this one through. So oxygen is element number 8, and its ground state electron configuration means that it should have 8 electrons, right? So we're going to have 1 S2, 2 S2, that's 4, 2 P, now we only need 4 more, so 2P4. So the oxide ion is going to have 2 more electrons. So add 2 more. And the resulting configuration is going to have 2 more than this oxygen in its normal neutral state. So it's not this one. That's not enough. That's just the oxygen atom on number 2. And this one corresponds to adding 2 more electrons. This would be something else that would be going beyond a stable noble gas configuration. This is the exact same configuration as, again, neon with 10 electrons. All right, those are simple examples of how the octet rule is used. I hope you find that easy to work with. Please ask questions if you need to know more.